Today we're going to talk about 5 of the most unusual planets discovered recently. Imagine a place where molten lava flows in an endless stream, creating a fiery landscape that glows red from space many light years away. Imagine a world so close to its star that its atmosphere is showered with a rain of vaporized metal. Imagine a giant planet orbiting a star so small that it defies our understanding of planet formation. It sounds like scenes from yet another science fiction movie. However, these are real discoveries that astronomers have made outside our solar system. Why is the planet literally melting from the inside out? What could cause strange light phenomena, including what may be the first rainbow seen outside our solar system? How do the system's tidal effects determine the fate of its planets? And finally, can a distant cold giant turn into a scorching hot Jupiter? Join us as we uncover the secrets of the strangest planets in the universe, each with its own story that could change the way we think about the cosmos. Get ready to encounter TOI 6713.01, recently discovered exoplanet that's caught the attention of astronomers for its unusual characteristics. This unique world, located about 66 light-years from Earth, has caught the attention of scientists with its intense volcanic activity and extreme surface temperatures. Discovered by the Transiting Exoplanet Survey satellite, this rocky planet is the innermost planet in its system, orbiting an orange dwarf star. With its size slightly larger than Earth, it completes its orbit in just 2.2 days, resulting in its shape being shaped by strong gravitational interactions with 2 neighboring planets. The gravitational pull from these nearby bodies distorts the planet's orbit, giving it an elongated shape that creates a phenomenon described as the perfect tidal storm. This constant attraction leads to intense internal friction and heating, resulting in surface temperatures in excess of 4,200 degrees Fahrenheit. Upon further investigation, astronomers speculate that the planet's surface is dotted with active volcanoes, and they're constantly erupting and contributing to the fiery glow. Stephen Kane, an astrophysicist at the University of California, Riverside, expressed the awe that researchers feel at the prospect of such a planet. Due to its intense heat, it emits light in optical wavelengths, making it visible from space as a glowing sphere. Unlike any other exoplanet discovered to date, TOI 6713.01 offers new insights into how extreme conditions can affect terrestrial planets. The tidal forces operating here are unprecedented. In comparison, Jupiter's moon Io has significant volcanic activity due to gravitational interactions with neighboring moons. However, the object of our attention is subject to tidal forces that are estimated to be 10 million times stronger than on Io. And that results in completely different and more extreme geologic landscape. Here, volcanic eruptions are not just a spectacular sight, but an opportunity for scientists to understand more about the formation and evolution of planets under extreme conditions. This dynamic behavior opens a window into how energy from both the proximity of stars and gravitational interactions can shape a planet's geological landscape. By measuring the planet's mass, researchers hope to gain insight into its material composition, volcanic activity, and history of formation. Future observations will be crucial to confirm its existence and detailed characteristics. As new data becomes available, this unusual world may change existing models of planet formation and evolution. And now let's be introduced to the equally amazing LHS 3154b, a massive exoplanet orbiting a surprisingly small star, poses a major challenge to our understanding of planet formation. With a mass about 13.2 times that of Earth, LHS 3154b resembles Neptune. Yet, it exists inside a planetary system whose host star, LHS 3154, has only 11% of the Sun's mass. The stark contrast raises fundamental questions about how such a large planet could form near such a low-mass star. The discovery of this planet was facilitated by the Hobby-Eberly telescope at McDonald Observatory in Texas. Using a cut-edge near-infrared spectrograph, the researchers found periodic shifts in the spectrum of the star, indicating the gravitational influence of the planet, which allowed to confirm its existence with observations from NASA Transiting Exoplanet Survey satellite and the European Space Agency Gaia satellite. Prior to the discovery of LHS 3154b, it was commonly assumed that low-mass stars form mostly small planets. Observations of other such M dwarfs often revealed clusters of rocky planets, such as in the TRAPPIST-1 system, where 7 Earth-sized planets orbit a low-mass star. However, LHS 3154b breaks this paradigm by showing a single imposing planet in a close orbit, suggesting an entirely new formation mechanism. The nature of this planet is suggestive of its formation. Although giant planets orbiting low-mass stars do exist, they usually appear much farther away from their stars, where different processes are at work. In our case, scientists considered the possibility that the planet formed in another system and was then captured by LHS 3154. However, the circular orbit of the planet fundamentally disproves this theory, indicating that its formation most likely occurred within the current system. Faced with these problems, the researchers turned to the core accretion model, which is traditionally used to explain the formation of planets. The initial modeling did not yield results consistent with the size and orbit of LHS 3154b, indicating that traditional models are not applicable here. Adjustments to the model parameters, in particular increasing the dust density in the proplanetary disk, led to a breakthrough. A 10-fold increase in the dust density provided the necessary conditions for the formation of a planet of similar mass in a close orbit. The realization highlights the potential phenomenon of missing mass in protoplanetary disks. The dust necessary for planet formation may exist in forms or states that modern telescopes cannot detect. That raises questions about the material available for planet formation in such systems. One hypothesis suggests that when dust aggregates, it may reach sizes beyond what can be discerned. Alternatively, disks may continually replenish dust by scooping it up from the surrounding cloud of material. This discovery prompts a reevaluation of theories of planet formation. It also emphasizes that planetary formation may be more diverse than previously thought and suggests that giant planets may indeed form in environments previously thought to be unsuitable. Another equally unique planet, WASP 76b, often referred to as the Hell Planet, is a prime example of the extreme conditions found outside our solar system. Located about 637 light-years from Earth, this exoplanet has attracted attention for its strikingly high temperatures and intriguing atmospheric phenomena, including the potential detection of Glory, a rare rainbow-colored light show. First discovered in 2013 as part of the Wide-Angle Search for Planets project, WASP-76b has a mass about 90% greater than Jupiter's, but with a diameter only twice as large. Such enormous size contrasts with its proximity to its host star, where it orbits at a distance about 20 times closer than Mercury is to the Sun. As a result, the planet completes a full orbit in just 1 day, 19 hours, resulting in extreme atmospheric conditions. The planet's tidal locking means that one side of the planet is constantly flooded with sunlight, while the other side is in darkness. The sunlit side reaches staggering temperatures of about 4,350 degrees Fahrenheit. Such intense heat can vaporize metal like iron, creating a unique atmospheric cycle. Vaporized materials can condense into rain on the cooler, darker side. This interaction of heat and atmospheric conditions creates a hostile but mesmerizing environment. Recent studies have revealed intriguing new data about the atmosphere of WASP-76b. In particular, a bright spot at the boundary between the illuminated and dark sides has been detected. This phenomenon has been interpreted as a potential glory, a rare optical effect characterized by concentric rainbow rings resulting from diffraction. Such a phenomenon has only been recorded within our solar system, making the possibility of observing it on such a distant planet particularly exciting. Glory is formed when sunlight passes through small gaps between atmospheric particles, bending and splitting the light into its constituent wavelengths. The conditions required for this phenomenon are very specific. The particles must be spherical, homogeneous, and stable enough to persist for long periods of time. Presence of such conditions on WASP-76b, while not certain, would mark a significant advance in our understanding of exoplanet atmospheres. Despite the possible identification of glory, researchers caution that the evidence remains preliminary because it is based on an exceptionally weak signal. More advanced instruments, such as those aboard the James Webb Space Telescope, may be needed to confirm this intriguing theory. Further observations could help astronomers determine if this is indeed a glory, thus opening a new chapter in the study of exoplanets. If the phenomenon is confirmed, it would not only be a groundbreaking discovery, but could also serve as a model for studying similar phenomena on other exoplanets. While researchers continue to study WASP-76b and its unusual atmospheric conditions, the possibility of detecting the first known rainbow outside our solar system remains a tantalizing prospect. Meanwhile, let's take a look at another intriguing planetary system that demonstrates the fascinating interplay of gravitational forces and their long-term effects on planetary orbits and environments. This is HD 104067. Located about 20 parsecs from Earth, this system includes a bright K dwarf star around which 3 separate planets orbit. Interactions between those planets result in noticeable tidal effects, particularly on the innermost of the planets. Initially a giant planet in an eccentric orbit with a period of about 55 days, was discovered in this system, and it was later confirmed that this planet, labeled B, has a slightly eccentric orbit. Later observations using radial velocity data from the high-accuracy radial velocity planet searcher and the high-resolution Echelle spectrometer detected an additional planet with a mass close to that of Uranus, orbiting the star every 14 days. In addition, data from the transiting Exoplanet Survey satellite indicate the presence of an Earth-like planet candidate with an orbital period of about 2.2 days. These are significant dynamical interactions between the planets in the system, resulting in pronounced tidal effects, especially for the innermost of the planets. The eccentric orbits of the two outer planets causes changes in the eccentricity of the inner planet's orbit, creating a so-called tidal storm. This phenomenon generates tremendous internal friction and heat within the planet, resulting in surface temperatures that can reach an incredible 2660 Kelvin, or in simple terms, 4,220 degrees Fahrenheit. The dynamical stability of the HD-10 4067 system has been thoroughly analyzed with simulations, which show that the system maintains long-term stability over millions of years. Continued studies of tidal effects and planetary interactions may provide insights into the formation and evolution of compact multiplanetary systems. And now the last but not least guest on our list for today. The exoplanet discovered this year with the complex name you see on the screen offers a glimpse into the dynamic and transformative nature of planetary evolution. This Jupiter-sized planet, located about 1,100 light-years from Earth, has one of the most highly eccentric orbits ever observed. It's currently undergoing a significant orbital transformation, changing from a cold Jupiter to a hot Jupiter over billions of years. Discovered thanks to data collected with the same tests, the planet was first identified by characteristic dips in starlight as it passed through its host star. Subsequent observations confirmed its highly elliptical orbit, which brings the planet close to its star and then deflects it far out into space. The orbit's not only eccentric, but also retrograde, that is, it moves in a direction opposite to the rotation of the star. The extreme nature of the orbit provides valuable insight into the processes that form hot Jupiters. Scientists believe that many of these planets begin their existence as cold Jupiters, forming in distant, harsh, frigid regions of their star system. Over time, gravitational interactions, especially in binary star systems like the one which this planet's located, can cause their orbit to become highly eccentric. The process, known as high eccentricity migration, is where a planet's orbit gradually shrinks and becomes more circular as it interacts with its stellar neighborhood. The binary nature of the host star system plays a crucial role in its orbital evolution. The primary star around which the planet orbits is itself orbiting the secondary star. The complex gravitational interaction causes significant perturbations that gradually change the planet's orbit. Modeling by researchers from MIT and Penn State University suggests that these interactions will eventually cause the planet to enter a narrow circular orbit characteristic of hot Jupiters. TC 2412-49530b's current elliptical orbit results in dramatic changes in temperature and radiation levels throughout its journey. When the planet is closest to its star, it experiences intense heating, which likely causes major atmospheric changes and extreme seasonal variations. This discovery not only adds to our understanding of the formation of hot Jupiters, but also once again emphasizes the diversity and complexity of exoplanetary systems. From the incredibly orbiting to the dramatically flaming, the universe is full of unusual planets that challenge our understanding of their formation and dynamics. Continue exploring with us to delve deeper into the mysteries of the strangest planets in the universe and learn more about the fascinating process that shapes the cosmos. In the vast expanse of our solar system, among the swirling gas giants and rocky Earth-like planets, an intriguing world lurks, a world larger than the planet Mercury, but orbiting not around the Sun, but around the colossal planet Jupiter. This is Ganymede, the largest satellite in our solar system. Ganymede, covered in a thick, icy shell, has attracted scientists for years. Its battered and scarred surface tells a story that's been billions of years in the making, a story we're only beginning to unravel. Beneath its icy exterior, Ganymede hides secrets that could forever change our view of life in the universe. It's currently the only known moon that has its own magnetic field, and deep beneath its surface, there may be more water than all of the Earth's oceans combined. Today we take a trip to this distant moon. We'll study its recent images and delve into the mysteries these images have begun to reveal. Our story began more than 4 centuries ago in 1610, when a man named Galileo Galilei pointed his primitive telescope at the night sky. He discovered 4 points of light orbiting the giant planet Jupiter that forever changed our view of the universe. These were Galileo's satellites, and the largest among them was Ganymede. Galileo's observations of these Galilean moons revolutionized our understanding of the cosmos by providing the first evidence that not all celestial bodies revolve around the Earth. Ganymede is the Titan among the satellites. Its diameter is about 3,273 miles. It is the largest moon in our solar system, surpassing even the planet Mercury in size. But size isn't the only thing that sets Ganymede apart. Transported to present day, our ability to study Ganymede has kept pace with technological advances. Modern telescopes, both ground-based and space-based, have given us a clearer picture of this distant moon. But it was the advent of space probes that really ushered in a new era of exploration. Spacecraft such as the Galileo Orbiter and the Juno probe have traveled to the Jupiter system to send back to Earth detailed images and data that have allowed us to study Ganymede like never before. These missions have given us a close-up view of Ganymede's surface, revealing its icy terrain and the intriguing patterns etched on it. Ganymede is a moon of contrast. Its surface is a patchwork of 2 different types of terrain. Darker areas filled with craters and grooves tell of the moon's turbulent past, while lighter areas hint at dynamic and geologically active world. An equally tantalizing aspect of Ganymede lies beneath its icy surface. Scientists believe there is a vast ocean of liquid water beneath the ice, containing more water than all of the Earth's oceans combined. Zeus, known as Jupiter in Roman mythology, took a beautiful mortal boy to become the cupbearer of the gods. This boy's name was Ganymede. It seems appropriate that the moon carries such a large amount of water around Jupiter. But perhaps the most intriguing feature of Ganymede is something we can't see. It's the only moon in our solar system that generates its own magnetic field, a trait usually reserved for planets. This magnetic field creates beautiful auroras in Ganymede's rarefied atmosphere, a sight truly worth seeing. The question arises, could this distant, icy world harbor the conditions necessary for life? Our understanding of Ganymede has been greatly enhanced by the daring missions sent to the Jupiter system. One of the most significant of these was the Galileo mission launched by NASA in 1989. Galileo arrived at Jupiter in 1995, embarking on a nearly 8-year mission to study the gas giant and its satellites. The spacecraft made several close flybys of Ganymede, taking detailed pictures of its icy surface and measuring its magnetic field. The data collected by Galileo revolutionized our understanding of Ganymede, revealing its complex geological history and confirming its magnetic field. This feature distinguishes it not only from other satellites, but also from most planets. Ganymede is the only satellite in our solar system that generates its own magnetic field. The magnetic field is created by the movement of molten iron in the core of the celestial body, a process similar to that which generates the Earth's magnetic field. However, the main mystery is that judging by the structure of the satellite and its age, the core of Ganymede long ago should have cooled and solidified. But still, how does the moon create a magnetic field? The answer may lie in a process called tidal heating. As Ganymede orbits Jupiter, the planet's gravitational pull causes the moon's interior to contract and stretch. To understand tidal heating, let's think about a simple everyday activity: kneading dough. When you knead bread or pizza dough, you're exerting force on it, pushing and pulling in different directions. As you work with the dough, you may notice that it begins to heat up. This is because the force you are applying creates friction within the dough, and friction generates heat. That's very similar to how tidal heating works. In the case of Ganymede, the kneading is done by Jupiter's gravitational pull. As Ganymede rotates around Jupiter, the planet's gravity attracts different parts of the moon with different forces, causing it to bend and stretch. This bending and stretching creates friction within Ganymede, and as with dough, the friction generates heat. This heat could be enough to melt part of Ganymede's interior, creating a layer of liquid metal that would generate the moon's magnetic field. Among other things, Ganymede's magnetic field is unique in that, unlike Earth's, it's embedded in Jupiter's powerful magnetosphere, creating a complex and dynamic electromagnetic environment. This magnetic field is important for the potential habitability of Ganymede. It creates a magnetosphere around Ganymede that could theoretically protect life on the moon from harmful solar radiation. In addition, the interaction between Ganymede's magnetic field and Jupiter's magnetosphere produces auroras in Ganymede's thin atmosphere. These auroras have provided scientists with valuable information about the internal structure of Ganymede, for example, confirming the presence of an ocean beneath its surface. More recently, the Juno spacecraft has been studying Jupiter and its satellites. Launched in 2011, Juno's primary mission is to study Jupiter's composition, its gravitational field, magnetic field, and polar magnetosphere. In June 2021, NASA's Juno spacecraft made a close flyby of Ganymede, coming within 645 miles of the moon's surface, taking images of the moon's surface to date. The spacecraft's JunoCam imaging system had only 25 minutes to take images of Ganymede, but in that short time, it managed to take 5 stunning exposures. Interesting fact: initially, during development, Juno was not equipped with a camera. It was project manager Scott Bolton who insisted, "We've got to put a camera on this thing." And it was indeed a wise decision. These images show Ganymede's complex and intriguing surface, with a mix of darker areas and strong craters and lighter areas and grooves and patterns. The Juno science team is now comparing these images with those from previous missions, looking for any changes that may have occurred over the past 2 decades. But taking these pictures wasn't easy. Juno had to rush past Ganymede at 12 miles per second and then glide over the tops of Jupiter's clouds at 36 miles per second. Nevertheless, despite these challenges, the spacecraft managed to take clear and detailed images of Ganymede, giving us an unprecedented view of this fascinating moon. These images are not only visually stunning, but they're also key to understanding Ganymede's geology and the potential for life. For example, the images show light and dark areas on Ganymede's ice shell, indicating differences in the purity and composition of the ice. This information can help scientists understand how Ganymede's ice shell formed and how it's changed over time. So let's take a closer look at the dynamic geologic history of this moon. The dark regions are considered the oldest parts of Ganymede's surface, some 4 billion years old. They are heavily cratered, indicating they have been relatively stable for a long period, bearing the scars of countless impacts. In contrast, the lighter colored groove regions are younger and indicate more recent geologic activity. These regions are mottled with intricate patterns of ridges and ditches, some of them more than a mile high and hundreds of miles long. These furrowed landforms are thought to have formed as a result of tectonic activity caused by the previously mentioned tidal heating from Ganymede's elliptical orbit around Jupiter. When the moon bends and stretches under Jupiter's gravitational pull, it releases heat that can cause the ice to crack and regenerate. This process can create faults and cracks in the surface, resulting in the ridges and grooves we see today. It is a process similar to plate tectonics on Earth, but in a much colder and alien environment. Thus, by studying these geologic features, we not only learn about Ganymede's past, we also gain insight into geologic processes that may occur on other icy moons and planets, helping us to understand the diversity of worlds in our solar system and beyond. As we delve deeper into the mysteries of Ganymede, one question arises: could this icy moon harbor life? While we don't yet have definitive answers, some features of Ganymede make this a tantalizing assumption. First, it's believed that Ganymede has an underground ocean of liquid water more than 100 kilometers deep. This ocean is warmed by heat generated with tidal bends. On Earth, wherever we find water, we find life. So the presence of a vast ocean on Ganymede opens up the possibility of life there, perhaps in an environment similar to Earth's deep-sea hydrothermal vents. These vents, spewing mineral-rich water heated by the Earth's interior, are teeming with life forms that thrive in extreme conditions. Could similar vents exist on Ganymede, providing the conditions necessary for life? Second, Ganymede's thin oxygen atmosphere, although not suitable for human respiration due to the low density, could potentially support some forms of microbial life. On Earth, some microbes are known to survive in extremely rarefied atmospheres, such as those at high altitudes of mountains. Although conditions on Ganymede are harsh and very different from those on Earth, life as we know it has proven to be incredibly adaptable and able to survive in a wide variety of environments. Thus, the possibility of life on Ganymede, while somewhat speculative, cannot be ruled out. As future missions explore this fascinating satellite in more detail, we may yet find answers to these questions. Who knows what secrets Ganymede may reveal? However, it's very important to be aware of the challenges and limitations of exploring such a distant and alien world. First, the sheer distance. Ganymede orbits Jupiter, which is about 484 million miles from Earth. Even traveling at the speed of light, it takes more than 40 minutes for a signal to travel from Earth to Ganymede and back. This makes real-time control of spacecraft impossible, and means that missions to Ganymede must be able to operate autonomously for long periods. In addition, the harsh conditions of Ganymede itself make themselves felt. The surface temperature of negative 276 degrees Fahrenheit, and it's exposed to intense radiation from Jupiter's magnetosphere. Any spacecraft that visits Ganymede must be designed to withstand these extreme conditions. And finally, there's the problem of interpreting the data we're getting. Images and other data from Ganymede must be transmitted hundreds of millions of miles through space and then analyzed by scientists on Earth. This process requires sophisticated technology and expertise, and there's always some degree of inaccuracy involved. It's not to say that current interpretations are wrong, but rather our understanding of Ganymede is constantly evolving as new data is collected and analyzed. Although the scientific community seems to be in general agreement on the main features of Ganymede, there's also some uncertainties. One major point of contention is the source and nature of the plumes observed on Ganymede's surface. Some scientists believe these plumes are caused by water from the interior of the moon being pushed through its icy crust, similar to the plumes observed on Saturn's satellite Enceladus and possibly Jupiter's satellite Europa. Incidentally, we've already debated whether there is life on Europa in another video. Similarly, while the existence of subsurface ocean on Ganymede is supported by several lines of evidence, the exact properties of this ocean, such as depth, composition, ability to harbor life, all still the subject of ongoing research and debate. Despite these challenges, our quest to explore Ganymede and other distant worlds continue. Each challenge we overcome brings us one step closer to understanding our place in the universe. As we traveled through the mysteries of Ganymede, it became apparent that our exploration of this fascinating satellite is far from over. NASA and other space agencies around the world have ambitious plans to explore the Jupiter system. The European Space Agency's JUICE, their mission launched April 14, 2023, from the Guiana Space Center on an Ariane 5 launch vehicle, and it will make detailed observations of Ganymede and other Galilean moons, Europa and Callisto. The Jupiter Icy Moons Explorer will be equipped with a suite of 10 advanced instruments capable of studying the surface and interior of Ganymede with unprecedented precision. It'll map the moon's icy envelope and underlying ocean, study the composition of its surface and atmosphere, and further explore its unique magnetic field. Beyond JUICE, there are proposals for even more ambitious missions. These include landers, rovers, and even submarines to explore Ganymede's ocean. While still in the conceptual stage, these missions represent the bold, innovative thinking that will be required to fully unlock the secrets of Ganymede. As we look to the future, one thing is clear. Ganymede remains a tempting place for scientific exploration. Its unique geology, magnetic field, and potential for life make it a solid target in the ongoing quest to understand the workings of the solar system and our place in it. In the veiled depths of the solar system lies an enigmatic mystery, Neptune's elusive moon, Triton. Buried in darkness, this seemingly lifeless moon hides features that defy explanation. Unlike other satellites, Triton orbits Neptune in the opposite direction to the normal one, defying the cosmic order. Its cold surface, surprisingly young, occasionally flashes with cryolava, revealing an otherworldly dynamism. But beneath the ice, shrouded in mystery, lies a dense layer that could be covering a bottomless ocean. A realm where extraterrestrial life may be kept secret. Come with us on this extraordinary odyssey to the outer reaches of the solar system. Ready for a cold but exciting journey into the unknown. Neptune, a blue icy giant pierced by endless ultrasonic winds, is one of the most distant planets in our system, not counting Pluto. It is the only planet we cannot see with the naked eye because of its dimness. 14 satellites are orbiting the icy giant along with Triton. The strange icy satellite was first discovered in 1846 by British astronomer William Lassell through mathematical calculations rather than direct observation, due to the imperfect optics for such distant objects at the time. Triton immediately attracted the attention of the scientific community because of its differences from other satellites. All of them are much smaller and, except for some outer satellites, move in their orbit in the direction of the planet's rotation, while Triton rotates in the opposite direction, or retrograde. In particular, scientists have noticed that the satellite is unusually similar to the famous dwarf planet Pluto. Their masses, diameters, and even the materials that make up the surface are very similar. But we'll talk about what role this plays for Triton a little later. The diameter of the unique satellite is 1,680 miles, which is almost 7 times larger than the second largest satellite of the ice giant Proteus. This size allows it to maintain a thin atmosphere, which is mainly composed of nitrogen and methane. On top of that, the satellite's upper atmosphere has an ionosphere, a place where atoms and molecules are ionized, and more intensely than on Earth. These factors are crucial for suggesting that Triton, like Pluto, may also be an icy dwarf planet. In addition, the ratio of rock to ice on the satellite is in the range of 70 to 30. This adds even more evidence to the planetary nature of Triton, and in particular hints at a different origin from all other satellites. It is therefore suspected that, like the Earth, Triton has a crust, a liquid mantle, and a rocky core. Because of its distance of 2.793 million miles from the Sun, Triton is one of the coldest satellites in the solar system. The average temperature there reaches -400 degrees Fahrenheit. The surface of the satellite is covered with a layer of frozen nitrogen, under which there's a thick layer of ice mantle. All of this gives it an icy luster that reflects about 70% of the sunlight that hits it over a long period. In particular, its surface may be quite young, which also hints that Triton is not a dead stone at all, but a rather geologically active planet. Triton has a very interesting dynamic history of its surface development. Its outer layer has many small impact craters, although they should be much larger and deeper. This suggests that the satellite may be recovering. In addition, when you look at Triton in detail, you can see large ridges and valleys with complex patterns that look like the skin of a melon, and smooth black stripes in some parts of it. However, it does not seem that they could have been formed only by crashing space objects, because then Triton would be covered with huge impact basins. Therefore, astronomers have one possible answer to this characteristic landscape. A huge ocean may be hidden under the ice layer. Triton's surface is rejuvenated by a mixture of water and nitrogen that settles on its outer layer. But how does water appear on the surface? There are only two ways for water to fill the satellite's surface. Water can be poured out through strong meteorite impacts, or its eruption through volcanic plumes in the outer crust. This is also hinted at by Titan's amazing nitrogen polar caps. Their formation depends on cryovolcanism. But wait, how can water erupt on such a cold moon? Triton is strongly influenced by Neptune's gravitational pull, which deforms the satellite's core, causing tidal heating, which heats the water inside. In particular, solar heating can also be the cause of cryolava eruptions. Solar radiation passes through the ice, heating the subsurface nitrogen until it escapes through the crust. Water eruptions on Triton can last for more than a year, spewing tens of cubic kilometers of matter to restore affected parts of the surface. Heidi Hamel, a senior researcher at the Institute of Space Sciences, believes that such high geyser eruptions require a powerful source of heat and an ocean. However, the existence of the ocean has not yet been confirmed. There are several hypotheses about the nature of such a young surface. For example, heat from inside the satellite can melt pockets of nitrogen ice, which then erupt outward. In particular, cryovolcanoes may be fed by water not from the subsurface ocean, but simply from pockets of water in the crust. Triton raises many questions about its internal composition, and the only way to find out for sure whether Triton lives up to its name is through missions to the edge of the solar system. The first telescope to take detailed images of Triton was Voyager 2 in 1989. Flying over Neptune's north pole, Voyager bent its trajectory due to the giant's gravity to reach Triton. At a distance of 25,000 miles, almost at the altitude of geostationary satellites, the telescope captured the very first images of Triton's surface, and then departed forever into deep space. It's thanks to these images that we know so much about the mysterious satellite today. The Voyager mission provided a comprehensive characterization of the satellite, including its mass, atmosphere, and composition. For example, it was the mission to Triton that established that the atmosphere is dominated by molecular nitrogen with a small content of methane, which suggested that the satellite could be geologically active and gave rise to the study of the nature of eruptions. In particular, Voyager 2 proved that there are no oceans of liquid nitrogen on Triton's surface and showed the world the features of the satellite's surface. However, the mission to Triton saw only 40% of the satellite, its southern hemisphere, and only one side of it because the satellite itself is always turned with one side toward Neptune. Almost 33 years after Triton's first image, Space Telescope James Webb took a new equally impressive photo of Neptune and Triton, albeit at a much greater distance. Webb has captured the barely visible rings of Neptune and its 7 moons for a very long time, but the largest moon of the icy giant has taken all the attention. To the left of Neptune in the image, you can see a very bright star-like object, but it is Triton. Such an outburst of the moon confirms its shiny surface of condensed nitrogen, which reflects almost all the sunlight that gets there. Although the photographs taken over the past 30 years have greatly advanced our knowledge of Triton, they're still not enough to build a complete map of the satellite and answer the most intriguing questions. Therefore, more expeditions to Triton are needed to make sure that all the guesses are correct. Triton's unusual orbit seems particularly interesting for further research. As we've already mentioned, Triton is one of the few satellites that moves against the direction of Neptune's rotation. Retrograde motion, or counterclockwise motion of cosmic bodies, is rare. Only a few satellites in the solar system, like Uranus, Saturn, Jupiter, and Neptune, have retrograde orbits. Moreover, Triton is also tilted by 23 degrees compared to Neptune's flat path as it rotates. Usually this tilt and reversal of motion is the result of a collision with another body. Therefore, some other object could have collided with Triton in the past the same way and caused the retrograde motion. However, this version is not currently popular in scientific circles. In particular, this scenario does not explain the size and similarity of Triton to dwarf planets. So, what's the main reason for the satellite's alien nature? Neptune's orbit passes right on the border with the Kuiper Belt, a region of the remnants of the solar system and its actual border. It's there that the dwarf planet Pluto is located. There's another possible reason for the formation of a retrograde orbit of a space body. An independent object moving at a certain speed and direction can be captured by another body with a greater gravitational pull. And since it's difficult to model the conditions under which Triton could have formed organically around Neptune, scientists have concluded that Triton was probably captured by Neptune's gravity into its orbit. It's now believed that the satellite could have been an object independent of Neptune in the past, once part of a double planetary system like the Pluto-Charon pair. The gravitational pull of Neptune is much greater than the relationship between two gravitationally bound small objects, so Triton could have become detached from another space body, in part by changing its orbital velocity. In particular, it's believed that Triton was headed for a collision with the icy giant, but its companion planet could have brought it into Neptune's orbit, but was itself ejected from the solar system. But this lost planet was not the only victim of Neptune's gravitational pull. As we mentioned, 13 other satellites are orbiting Neptune. They can be divided into 2 groups, internal and external. And absolutely all of them have a very small mass. For example, Triton's mass is 99.5% of the mass of everything around the icy giant. Thus, Titan's migration could have destroyed Neptune's previous moons, leaving only small fragments behind. But this applies mostly to the inner group. The outer satellites could have been just as captured by Neptune as Triton, but the icy moon also left its mark here. The third largest moon, Nereid, has a highly elliptical orbit at perihelion. It approaches 858,400 miles, and at aphelion, it approaches 5,981,600 miles. It was probably knocked out of its normal orbit by a migrating Triton. Although it managed to escape the fatal collision, damaging other satellites, its retrograde orbit means that Triton is moving slower than the planet's rotation speed, which is why it's gradually being attracted by it. Therefore, in a few million years, the icy moon is likely to be torn apart by Neptune's gravitational forces, forming a new ring. But while this gloomy scenario is in the distant future, Triton has another interesting feature that's worth exploring now. Even though Triton is completely covered in ice, made of condensed nitrogen, the hypothetical ocean beneath this frozen surface layer could be warm and therefore harbor life. Water is a very important factor in the development of life. It serves as the main medium for many biological processes necessary for the birth of any living organisms we know, such as maintaining cellular structure. The ability to form life on Triton is influenced by several other important factors. For example, in addition to geysers that spew subsurface nitrogen, Voyager noticed another strange, dark cryovolcanic plume during its expedition. The unusual black color of the 5-mile-high plume is likely due to carbon-rich materials. Carbon is the basic building block for the formation of an organism from the simplest to the human-like. It is currently impossible to determine the exact composition of the hypothetical ocean, but scientists at the American Astronomical Society believe that Triton's ocean depends on the volatile composition of comets and therefore may contain a lot of ammonium, sodium, chloride, and oxygen. However, Triton is very cold, so it is unlikely that complex life as we know it could exist there. Furthermore, although the satellite has a nitrogen atmosphere, just like on Earth, it's very thin, so it will not be able to retain enough heat even with the help of nitrogen clouds in the upper layers. However, the temperature on Triton's surface can still rise, although not to very high levels. In 2010, scientists using the Very Large Telescope of the European Southern Observatory discovered that Triton also has seasons, just like on Earth. But they last not 3 months, but 40 years each. Currently, summer is in full swing on the satellite. During this time, researchers from the Massachusetts Institute of Technology have found an increase in temperature from negative 392 Fahrenheit to negative 389 Fahrenheit. While this may seem like a small increase, it's a lot for a satellite that's so cold. That's why MIT professor James L. Elliott is confident that these are signs of global warming. For every 9 years, the temperature could rise by another 3 degrees Fahrenheit. This means that the evaporated gas could have joined the atmosphere during this period and increased its volume. However, on Triton, the atmosphere cannot be constantly saturated. In the harsher fall and winter months, it will begin to thin until it freezes and settles on the surface. That is, in winter, the atmosphere on the satellite is simply absent and will appear only after it warms up in the spring. Include the possibility of simple, primitive life developing in the water of the satellite. Still, to check for sure whether Triton can answer the question, "Are we alone?" a photo of Voyager and James Webb is not enough. Triton raises a lot of questions, remaining without understatement one of the most intriguing satellites in the solar system. And despite all the difficulty of flying to such a long distance, the curiosity of science still wins out to a certain extent. In the near future, a new proposed Trident mission from NASA was planned for Triton, which would last about 16 years, revealing the secrets of Triton and Neptune. The main goal of the mission was to study the factors that determine the habitability of the satellite as confirmation of the existence of a subsurface ocean and molecular building blocks. In addition, Trident would explore the remaining 60% of the satellite surface, allowing scientists to see the entire geographical picture of Triton. However, Trident failed to win the grant for the 2021 launch, losing out on 2 other missions, Da Vinci Plus and Veritas, which are going to explore Venus. Still, all is not lost for the mysterious Triton. China's also currently considering a nuclear-powered mission to Neptune. In particular, it's possible that NASA will reconsider Trident for an expedition in the future. Trident could reveal more important information about ocean worlds and their geology, Expeditions to Neptune's largest moon could not only find evidence or refute the presence of an ocean there, but if it is present, establish its approximate composition to better understand the possibility of life on the cold moon. The study of such hypothetical and sometimes active ocean worlds as Triton, Mimas, Enceladus, or Europa can change all our ideas about the origins of life and about objects with extreme conditions in general. Therefore, future expeditions will advance our knowledge greatly, closing many of our questions and opening up new mysteries for us. Perhaps soon enough, we'll be able to answer the questions of how global oceans form on icy planets and satellites, what makes them geologically active, and finally, whether we are alone. All thanks to the mysterious, cold Triton. Have you ever wondered if some of the most exciting scientific discoveries can be made from data stored for decades? That's exactly what happened when NASA's Magellan spacecraft took pictures of Venus more than 30 years ago. At the time, scientists were focused on mapping the planet's surface and studying its dense atmosphere. But what they didn't realize was that they were capturing something far more extraordinary. Images taken more than 30 years ago led to a sudden discovery. Beneath the dense, poisonous clouds of Venus, all this time lay a great fire secret: active volcanoes. This groundbreaking discovery changes our understanding not only of Venus, but also of other planets in our solar system and beyond. The second planet from the Sun is often called Earth's evil twin because of its similar size and composition. However, while Earth is a refuge for life, Venus is a planet of extremes. With a diameter of about 7,521 miles, Venus is almost the same size as Earth, but it's much closer to the Sun, with an average distance of about 67 million miles, which is about 1/8 closer than our home planet. This proximity means that Venus has a much hotter environment than Earth, with surface temperatures that can reach 880 degrees Fahrenheit. This makes it the hottest planet in our solar system, even hotter than Mercury, which is much closer to the Sun. One of the key factors contributing to Venus's high temperatures is its dense atmosphere, consisting mostly of carbon dioxide and nitrogen. This atmosphere creates a powerful greenhouse effect, trapping heat and causing temperatures to rise. In addition, the dense clouds of sulfuric acid that envelop the planet contribute to its intense heating. Despite its harsh conditions, Venus has long fascinated scientists who have sought to study its unique characteristics and understand its history. Over the years, researchers have made many discoveries about Venus, including the fact that it is the only planet in our solar system that rotates clockwise on its axis. Moreover, the atmosphere of Venus is dominated by the rapid rotation of the cloud layer, which rotates much faster than the planet itself. This zone rotates in just 4 Earth days, while the planet itself takes a leisurely 243 days to complete a full rotation. Both rotations occur in retrograde direction, defying the norms of the solar system. In the context of Venus, this means that the planet and its atmosphere move in a direction opposite to the rotation of the Sun and most other planets in the solar system. Now, this natural convectional motion, known as superrotation, begins at about 6 miles and steadily increases up to 40 miles, where the equatorial winds reach a terrifying speed of 335 miles per hour, gradually slowing down as they climb to higher altitudes. It seems that the atmosphere of Venus, or at least the cloud layer, rotates about 50 times faster than the planet itself. And this fascinating phenomenon probably influenced the rotation of the planet. But here's the catch. The mass of Venus's atmosphere is only 1/10,000th of the planet's mass. So how could that be? There must have been an exchange of velocities between the planet and the atmosphere to conserve total kinetic energy. The mystery remains unsolved. Also, despite the planet's scorching heat and harsh environmental conditions, the temperature on the planet's surface is almost constant and uniform due to the winds that sweep across its surface and ensure that heat spreads evenly. During the Venusian night, which lasts about 58 Earth days, the surface temperature drops only slightly. However, the temperature changes with altitude. The atmosphere at 62 miles ranges from positive 81 degrees Fahrenheit during the day to negative 225 degrees Fahrenheit at night. Venus's atmosphere is massive, more than 100 times the weight of the Earth's atmosphere. The huge mass of Venus's atmosphere also has great thermal inertia, which largely explains the homogeneity of the temperature on the planet's surface, in which one can observe an analogy with the water of Earth's oceans. Venus's atmosphere has a density of about 1/10 the density of water, which together with the corrosive composition of the atmosphere is responsible for a level of erosion comparable to a river. For all that, there's almost no wind at the planet's surface, barely exceeding the speed of a few miles per hour, being stronger at the equator and weaker toward the poles. They create a visible V-shaped structure in cloud layer images. However, much of Venus's prehistory remains a mystery. For example, although it's known that the planet formed about 4.5 billion years ago, it's unclear how it evolved to become the hot, hostile world we know today. Some scientists speculate the volcanic activity may have played a significant role in the shaping of the planet's environment, with eruptions releasing gases that contributed to the dense atmosphere we see today. Over the years, scientists have made many observations of Venus from both Earth and spacecraft. Some of the earliest recorded observations date back to ancient times, when astronomers such as the Greek philosopher Pythagoras and the Roman poet Ovid documented their observations of Venus in the night sky. However, it wasn't until the 20th century that scientists were able to study Venus in more detail. In 1961, the Soviet Union launched the first spacecraft to visit Venus, called Venera 1. Although the spacecraft could not successfully land on Venus, it provided valuable data on the planet's magnetic field and radiation environment. Subsequent missions, including the Soviet Union's Venera and Vega missions and the U.S. Mariner and Magellan missions, provided even more detailed data on Venus. Despite these successes, however, the study of Venus has proven to be a major challenge for scientists. The planet's dense atmosphere makes it difficult to see its surface, and its harsh conditions make it difficult for spacecraft to exist for long periods of time. The Soviet Union's Venera 13 landing module, which successfully landed on Venus in 1982, lasted only about 2 hours before falling victim to intense heat and pressure. NASA's Magellan spacecraft arrived at Venus in 1990 and spent 4 years mapping the planet's surface with radar. The spacecraft collected an enormous amount of data, including detailed images of the planet's surface and data on its topography, gravity, and magnetic fields. Only more than 30 years later, in 2021, scientists made an incredible discovery when they reanalyzed the data collected by Magellan: the presence of active volcanoes on Venus. The discovery was made by a team of researchers led by Anna Gilcher of the Institute of Geophysics at the Swiss Federal Institute of Technology in Zurich. The researchers analyzed Magellan radar data and identified features on the surface of Venus that suggested the presence of recent volcanic activity. The team also examined images taken by the spacecraft and found evidence of lava flows and other volcanic features. But how did scientists determine the presence of active volcanoes on Venus from data collected more than 30 years ago? One key factor was the use of new imaging techniques and algorithms that allowed researchers to extract more detailed information from the data collected by Magellan. By analyzing radar data, the researchers were able to identify changes on the surface of Venus that were probably caused by volcanic activity. They also found evidence of elevated surface temperatures in the same locations, further supporting the idea that there are active volcanoes on the planet. Moreover, quite recently, in March of this year, scientist Robert R. Herrick of the Geophysical Institute, University of Alaska Fairbanks, and Scott Hensley of the Jet Propulsion Laboratory, California Institute of Technology, conducted a similar study. In an article in Science, they discussed how volcanic activity on Venus has been obscured by the lack of observable eruptions. However, the authors used images from the same Magellan spacecraft to study volcanic areas on Venus. Thanks to images taken between 1990 and 1992, a manual search was conducted in areas previously identified as probable manifestations of active volcanism. The authors searched for volcanic formations like cones, vents, and lava flows that had appeared or changed between images. To create a detailed topographic map, they used a technique called stereoradargrammetry. They also made the images look as if they had been taken directly over the observation object using a process called orthogonal transformation. The paper also describes a direct simulation, distant view of images of the appearance of surface objects at different viewing geometries, which were then compared with similar versions of the images. As a consequence, they found that the vent of a volcano in the Atla Regio region had changed dramatically in less than a year. The same opening doubled in size and became deformed, with a lake of lava filling the edge 8 months later. This discovery may provide insight into the evolution of Venus and the differences between its landscapes and that of Earth, since it was originally thought that the surface of Venus, like that of Earth, had water. However, it's not entirely clear whether volcanism is currently active or not. The low level of detection suggests that Venus is less volcanically active, even Jupiter's satellite Io. Only about 1.5% of the surface area of Venus has been studied, given the missing and poor data. The recent discovery of active volcanoes on Venus is a breakthrough of great importance to the field of planetary science. One major implication is that it challenges the common view of Venus as a geologically dead planet. The presence of active volcanoes means that Venus is still geologically active, which opens up new possibilities for studying the formation and evolution of the surface of rocky planets. Another potential consequence of the discovery of active volcanoes on Venus is the possibility of detecting microbial life on the planet. Volcanic activity on Earth is often associated with the presence of microbial life, and the same may be true on Venus. Although conditions on Venus are harsh, with temperatures high enough to melt lead and a dense atmosphere of carbon dioxide, it is possible that microbial life may have adapted to survive in those extreme conditions. As for future research missions, the discovery of active volcanoes on Venus has already generated considerable interest among planetary scientists. There are plans for future missions to Venus, such as the Veritas and Da Vinci Plus missions. The Veritas mission is led by NASA's Jet Propulsion Laboratory and will be launched within a decade to study Venus from its surface to its core to understand how a rocky planet the size of Earth took an entirely different path. The Veritas mission will use the state-of-the-art synthetic aperture radar to create three-dimensional global maps and a near-infrared spectrometer to determine surface composition. The spacecraft will also measure the planet's gravitational field to determine the structure of Venus's interior. The Da Vinci Plus mission, on the other hand, is a complement to the Veritas. NASA plans to launch it to study the atmosphere and geology of Venus. While the Veritas orbiter will orbit Venus and capture data from the above, the Da Vinci descending sphere will descend through Venus's atmosphere to measure its composition as well as study clouds, winds, and surface features of the planet. The sphere will also capture high-resolution images of Venus's surface as it descends, providing valuable information about the planet's geology and geophysics. Unfortunately, there have not been many missions to Venus in the last 30 years. In fact, funding for planetary exploration has been cut, and new missions to Venus will not start until the 2030s. But with each discovery, we're one step closer to unraveling the processes that shaped our own planet Earth. In addition, the study of Venus provides valuable information about exoplanets outside our solar system. Because many exoplanets are similar to Venus, studying this planet can help scientists determine the potential habitability of other worlds. The recent discovery of active volcanoes on Venus is just the tip of the iceberg, but it underscores the importance and complexity of studying and analyzing large amounts of old data. Although this is just one event, the data may contain other discoveries waiting to be revealed. It is important to note that tools for processing and comparing large amounts of data were not available until recently. This provides a huge field for anyone interested in astronomy or planetary science to conduct their own research and make discoveries. Even without expensive equipment, anyone can contribute to this field by working hard and with dedication.